Good morning everyone, and welcome to Migrate your .NET API to AWS Lambda. My name is James Eastham and I'm a Cloud Infrastructure Architect at AWS Professional Services. I'm incredibly excited to spend time together this morning talking about .NET and Serverless. Let's get to it. So I'd like to start with quickly talking about a customer story that leveraged the power of AWS Lambda. The Financial Industry Regulatory Authority, or FINRA, is a not-for-profit organisation authorised by the US Congress to protect investors and ensure market integrity through effective and efficient regulation of broker deals. It writes and enforces rules governing the activities of more than 3,800 broker deals, representing more than 600,000 brokers. It examines firms for compliance, fosters market transparency, and educates investors. Every day, FINRA oversees up to 75 billion market events, 99% of equity trades and 65% of option trades in the United States. And they apply data analytics to uncover insider trading and other strategies used to gain an unfair advantage. FINRA recently moved a key part of its technology infrastructure to AWS, adopting AWS Lambda serverless computing to make data validation more efficient. So broker-dealers must submit daily data to FINRA, adding up to more than 50,000 files. As soon as the data is received, FINRA validates it to ensure it is complete and correctly formatted according to a set of more than 200 rules. The system performs up to 500 billion validations every single day, and that processing demand varies significantly over time and can even double or triple in response to market conditions that drive higher trading volumes. FINRA found 5 key benefits from adopting Lambda and Serverless. The first is that they increased the validation system cost efficiency by a factor of 2. They reduced their validation times from up to 7 minutes to less than 1 minute. They completely eliminated the management overhead of on-premise servers and infrastructure. And they achieved that easy scalability to meet the massively changing volume needs. And they implemented all of this in only 3 months. And that's a pretty incredible story. As part of FINRA's journey, they moved their traditional legacy compute to AWS Lambda, but this isn't something that can happen overnight. The move to a serverless backend requires a paradigm shift in the way you think about your applications. Now, I'm a developer, first and foremost, like a lot of you listening, but I always find it really valuable to understand the why before diving into the how and getting fingers on keyboard. So what exactly is modernization? Well, at a high level, we define modernization as the process of progressively transforming existing applications and infrastructure to extend to higher value cloud native services that unlock new business capabilities, accelerate innovation, and reduce your technical debt. Here at AWS, we like to think of modernization as a journey that includes enterprise compute, infrastructure and architecture patterns, people and process. We find most customers take an incremental approach to modernization. Increasing modernization also leads to an increase in economic value. From our customers' data, we typically see a 20% savings in the unit cost of a CPU cycle just by lifting and shifting to cloud infrastructure. As customers continue to optimize their cloud instances through right sizing and license optimizations, they typically see an additional 10 to 20% saving. By taking that a step further and adopting higher level modernization approaches and services like serverless, customers typically experience further cost savings, with many seeing savings of up to 60% or more. These savings can be redirected or reinvested into driving more innovation and value-added activities to your customers. Now, what are the reasons to modernize? Well, our goal at AWS is to help you innovate, and we think serverless is the way that you can get to market the fastest with the lowest total cost of ownership. When we think about where and how to innovate, we do it based on what will most help you innovate. We think serverless provides an incredible agility to developers. It allows them to quickly test out new features and functionality without the need to worry about provisioning servers. They can write some code, deploy and test it within minutes. It allows them to move extremely fast and innovate quickly. The removal of that undifferentiated heavy lifting that comes with managing servers and running your infrastructure allows your development teams to focus solely on the things that matter, delivering features to your customers. And all of that comes with extremely low cost of ownership. Lambda, for example, is built to the millisecond of the time your code is running. This is a paradigm shift from the server-based model where you may be running 20 servers 24/7, but only actually utilising a small portion of their full capacity. Serverless also provides excellent performance to meet a broad set of workloads. With Lambda, you can have memory up to 10 gigabytes, provision concurrency, and it also scales faster than any container orchestration system out there. As of March this year, Lambda now also supports up to 10 gigabytes of ephemeral storage. That opens up a whole new set of use cases for serverless around ETL and even some caching workloads. There's also a wide breadth of integrations with other AWS services. The available serverless services at AWS now cover a wide range of use cases, from compute to databases and even now to machine learning workloads. A large number of these services integrate seamlessly with each other and with AWS Lambda. And that's why serverless adoption is growing so fast. A serverless first strategy enables customers to focus on things that benefit their customers and not infrastructure management. We launched Lambda 7 years ago now, and today thousands of customers have built applications that already drive trillions of invokes per month, and Lambda continues to grow at a phenomenal rate. But serverless isn't all about Lambda. I know when I first got introduced to serverless and Lambda, I thought they were one and the same, but there's actually serverless services at all layers of the stack. And while Lambda offers a lot of key advantages, it's really when all these components surrounding Lambda work together that we start to see much bigger benefits. Lambda's a really great introduction to the world of serverless, as we're going to look at later in this presentation, but that isn't all there is to serverless. And customers are building a wide variety of applications with the serverless building blocks, but there's a few common areas where we tend to see huge benefits. So customers often start out with simple IT automation tasks, the kind of things you might traditionally run with a PowerShell script or a batch script. As this adoption of serverless grows, you may start to do some data processing tasks, so reacting to things in S3, for example, and doing some kind of data manipulation with that data. As experience starts to spread, teams start building entire microservice-based applications, APIs, back-end workers, all using completely serverless technologies. And with some of the recent releases to AWS Lambda, we're even now finding customers running machine learning workloads using Lambda and using serverless compute. I just want to touch on another customer use case quickly before we get into a bit more detail. Coca-Cola is a great example of how a serverless strategy enabled agility when they had to react to the COVID-19 pandemic. So they wanted to provide a touchless experience for some of their drink dispensers. And so they built a new smartphone app that allowed customers to order and pay for drinks without actually coming into contact with the vending machines. Because they built with Lambda, the team was able to focus on the application rather than the security, the latency, or the scalability. Since with Lambda, that's all built in. As a result, they built this new application in just 100 days, and now there's over 30,000 machines that have the touchless capability. So I've talked more generally about serverless up to this point, and I just quickly want to dive deep into Lambda itself before we get into the details of how to migrate your applications. So Lambda's biggest superpower is that it's completely event-driven. Lambda reacts to things that are happening in your system, and it lets you run code without the need to provision or manage servers. As I said earlier, you only pay for the compute time you consume to the millisecond, and there's no charge when your code isn't running. That per millisecond charge scales based on the memory allocated to your function. Now, it's important to note that a higher memory allocation does not always equate to a higher total cost, and there's lots of tools out there that can help you perform that cost-benefit analysis. You can run code for almost any type of application with Lambda, and Lambda just takes care of everything you need to run and scale your code with really high availability. Lambda functions are also versioned, so by default, the latest version of your function is always invoked. But you can add a set of aliases to a given function and set which version of a Lambda function is associated with each alias. So for example, you may have a live alias, a dev alias, and a UAT alias. Now the dev alias may always be associated with the latest version of your code, but your production alias may be only associated with a version that you know has been tested, integration tested, and been through the whole lifecycle to ensure that it's ready for your customers. And Lambda transparently supports load balancing, auto-scaling, up with workloads handling thousands of concurrent requests per second. And it does all of this whilst preserving security isolation due to the managed runtime environment model. Security and compliance is a shared responsibility between you and AWS. The shared responsibility model can help relieve your operational burden as AWS operates, manages and controls the components from the host operating system and virtualization layer down to the physical security of the facilities in which the service operates. Now, with traditional compute, you as the customer take on more responsibility for your infrastructure. Networking, OS patching, firewalls, amongst other things, are all your responsibility. Once you move to serverless and for AWS Lambda, AWS manages that underlying infrastructure and foundational services, the operating system and the application platform. You are responsible for the security of your code and identity and access management to the Lambda service within your function, but AWS handles the rest. This reduced responsibility for you as a developer allows you to better focus your time on providing things that matters, delivering features to your customers. Now, you may think, as I'm talking about Lambda, that there's lots of other compute options and lots of other ways to run applications on AWS, and you're absolutely right. And there are some pretty clear guidelines for when you would choose Lambda or when you would choose another compute service. So Lambda functions can only run for a max of 15 minutes, and there's no control of that underlying infrastructure. So if you have a workload that has a GPU heavy use case, for example, then Lambda may not be a good fit because you can't pick that underlying GPU heavy compute. If your code requires more than 10 gigabytes of memory, that would also move you away from Lambda. So Lambda execution environments are not long-lived, and I'm going to go into more detail on execution environments in a few slides' time. But if anything is stored in the local state, then it will be lost when the Lambda execution environment shuts down. Multiple requests to the same Lambda function may also be routed to different execution environments, which would then have different local states. So if you have any requirements to use local state or any kind of local storage, then Lambda may not be a good fit. There are also some limitations around simultaneous function executions and latency that may cause you to pick another of the available compute services. So there's three different ways that Lambda execution happens, all of which, as I said earlier, are triggered by events. An event source could be an AWS service, or it could be a developer-created application that invokes the function directly. The first execution model, and the most important for this conversation, is the synchronous-based model. And that's where a service or some application code invokes a Lambda function and waits for the response. In the case of API Gateway passes the HTTP request payload to Lambda as an event. Lambda will do some work and then it will return some information back to API Gateway, and API Gateway will then pass that back to the caller. The second model is the asynchronous invoke model, and that's where a Lambda function gets invoked and the Lambda service places that event payload into a queue. And then the Lambda function will then work through that queue in an asynchronous way. Typically that is instantaneous, but there can be a slight delay or a slight wait time for that invoke, and that is traceable using Amazon X-Ray. The third model is the poll-based model, and that's for things like SQS or DynamoDB streams or Kinesis streams. And that's where Lambda will poll the service on your behalf, and it will manage the retrieval of records, the invoking of your function, and then also the clearing down of them records after the fact. So for SQS, for example, the Lambda service will handle taking records from the queue, processing them records, and then also deleting the records from the queue after they've been successfully processed. Now, for the synchronous request response based invokes like from API Gateway, I just want to touch on how that works from an execution environment perspective. So when the request comes in, the request comes to the invoke service, and if that's unavailable, callers may temporarily queue the payload to retry the invocation a set number of times. If the invoke service receives the payload, the service then attempts to identify an available execution environment for the request and passes the payload to that execution environment to complete the invocation. If no existing or appropriate execution environments exist, one will be dynamically created in response to the request. while in transit these payloads are secured using TLS 1.2. Now, execution environments are reserved for a specific function version and cannot be reused across function versions. So as we talked about earlier, if you had different aliases and different versions, none of them same aliases would share the same execution environment. If you have two different versions, that will be at least two unique execution environments. And each execution environment may only be used for one concurrent invocation at a time, and they may be reused across multiple invocations of the same function version for performance reasons. Depending on a number of factors, for example, rate of invocation, configuration, and so on, one or more execution environments may exist for a given function version. With this approach, Lambda is able to provide function version level isolation for its customers. And these execution environments are continuously monitored and managed by Lambda, and they may be created or destroyed for a whole number of reasons. Now, customers can manage the number of pre-provisioned execution environments that exist for a version by configuring provision concurrency. When configured to do so, Lambda will create, manage, and ensure the configured number of execution environments always exist. This ensures that customers have greater control over startup performance at any scale. Other than through a provision concurrency configuration, customers can't deterministically control the number of execution environments that are created or managed by Lambda. Lambda also has some container image support, so you can package your application code in a container image up to 10 gigabytes in size, giving you the capability to run almost any workload using Lambda. A use case here would be on a machine learning workload. A packaged and trained machine learning model can be placed as part of your container image, which can then be used by the invoked Lambda function, and that keeps your application code right next to the trained machine learning model. Another benefit of the container image support is that if you as a developer are already familiar with tooling required to build and deploy container images, you can then use that same tool set to execute Lambda functions. An important point is that the container is merely a way of packaging your code. The code itself still needs to support the event-driven paradigm that Lambda has. You couldn't just reuse an existing container and run that in Lambda and expect it to work successfully. So now we've covered some of the background of serverless and AWS Lambda, it's time to get our hands dirty and look at how we can migrate your existing APIs to leverage serverless compute. And just before we get into that, I want to just talk about the Hexagonal Architecture pattern. And that pattern proposes the division of a system into loosely coupled and interchangeable components. The application and business logic sit at the core of the application. From there, the next layer up is a set of interfaces that handle that bi-directional communication from the core business logic to the implementation details, which are kind of at the outside and at the perimeter. The inputs, be that the API controllers, UIs, or test scripts, and outputs like database implementations and message bus interactions are right out at the perimeter. And what that means is that the chosen compute layer becomes an implementation detail, not a core part of your system. And it allows a much cleaner process for migrating to different databases, integrations, or to different compute layers. So something we're all familiar with, I'm sure, is the traditional three-tier application architecture. You have some form of web tier or presentation tier. There's the application server and the business logic layer, and then the database servers and the database layer. Now, this architecture is completely functional, but as we know, as you get to a certain scale, it doesn't enable you to move as fast as you probably want to. As we start to move to a more modern architecture, it does still look a lot like a three-tier architecture. There are a lot of the same elements here, like data, logic, and presentation, but there's also a few key differences. So this architecture on screen now is a single microservice performing a single business function. Many of our customers run dozens, hundreds, or even thousands of these services to improve the scalability and resilience. That differs from the traditional model where you would just have a fleet of application servers that are your entire application estate. The communication between layers also changes slightly. So here we're using a combination of events, messages, and queues that allow a resilient communication within your microservice and also between each service. And with this more modern approach, you also have a purpose-built data strategy. So rather than having a single monolithic database, you may choose a data provider that directly fits the use case of your application, your specific service. So the code examples I'm going to walk through for the rest of this presentation can be found in the GitHub repository on screen at the moment. And what that includes is a simple .NET Core API that receives API requests and performs CRUD operations against the MySQL database. It's a traditional monolithic API, albeit dramatically simplified for the purposes of demonstration. I do want to call out at this point that there's nothing inherently bad with a monolithic application. There's just many use cases where you get to a certain scale that you may want to start looking at different options. The API in question has 5 endpoints from a single booking controller that allows the retrieval, creation, update and deletion of bookings. As we move this architecture from a traditional approach to a more serverless and Lambda-based approach, it kind of looks like this. So there's still broadly 3 tiers. We've got a presentation tier, which happens to be API gateway. We've got the business logic layer, which is a set of Lambda functions, and then we still have the MySQL database as it was traditionally. Now, one of the real powerful things here is splitting the Lambda functions endpoints into separate functions. And that gives you a lot of power, because if you had a single API endpoint, as in the traditional API, and one of your endpoints is really resource intense, heavily used, or let's say has different permissions requirements, in the monolithic world, you need to increase the resources of the entire server or platform and give them permissions en masse. So let's say one endpoint needed to be able to communicate with an event bus, but the other API endpoints didn't. It would be really difficult to manage that permission set in a monolithic application. Now with Lambda, you can specify the resources and permissions at a per endpoint level, meaning you could increase the resources of, say, the post endpoint for reserving a booking, and therefore the per millisecond cost of that individual function, but that wouldn't affect the rest of your API endpoints, and they can still run at that nice, cheap, really low resource model. So if you're building a .NET Core API, I'm sure you're familiar with the dependency injection configuration on the left. A single configure services method is called as part of the startup process of your API, and that sets up the dependency injection container with all of the relevant interfaces and implementations. A lot of the boilerplate code that manages that configuration is hidden away in .NET itself. Now, it's still possible to use that same dependency injection framework when using Lambda. It's just that boilerplate code that the framework hides away just needs to be brought to the forefront. So as you can see on the right hand side code sample, the middle section is an exact replica of the normal .NET Core API startup. We still add the entity framework database context, we still add some of the HTTP clients and some of the interface implementations. All that's changed is we've just added some boilerplate code around that to create the service collection, to populate the service collection, and then also build that into a service provider that can then be used by the Lambda function code. There's also some slight differences as well with how the actual controllers work. So this example shows how you would use the dependency injection framework in your function code. So normally interface implementations are just injected as part of the constructor of your controller, as you can see on the left. Now in Lambda, we just manually need to call that configure services method, and then we can access the required interfaces from that public services property. Running this configure services method as part of the function constructor ensures that configuration only occurs once per Lambda execution environment. And then that same container can then be reused for later executions. Looking at the function code itself, you can see that the central part of the function is still the same. We still write a log message for the receive request, and then we execute the list for customer method from the iBooking repository. The difference is the surrounding code to validate and access the HTTP request variables. As I mentioned earlier, Lambda is completely event driven. The API request is passed to Lambda as an event payload, and that payload then needs to be manually read to pull out the relevant information. So there's a whole suite of NuGet packages available that simplify this payload mapping for things like SQS, DynamoDB, EventBridge, and as you can see on screen there, for API gateway proxy requests. The response also requires slightly more manual configuration. Instead of just returning an OK, we return an API gateway proxy response object. And with that object, we can manually then set the status code, the response body, and any additional headers that you need that will then be passed back to API Gateway, and then onto the caller that first called that API. So that covers dependency injection. So I'd now like to cover application configuration. So as we move applications through the software development lifecycle, the configuration from environment to environment will change. In a basic .NET application, this would normally work using settings provided in your app settings file. With Lambda, there are a variety of different options we have for managing function configuration. The first and simplest are environment variables. Lambda allows you to set environment variables against the function that can then be read from your application code. This is great for simple, non-sensitive information, but provides no way to encrypt or hide or manage the permissions to any sensitive data. And that's where AWS Secrets Manager comes in. Secrets Manager helps you protect secrets needed to access your applications, services, and IT resources. The service enables you to easily rotate, manage, and retrieve database credentials, API keys, and any other secrets throughout their lifecycle. Applications retrieve secrets with a call to the Secrets Manager API, completely removing the need to have stored information in plain text. It also offers secret rotation with built-in integration with Amazon RDS, allowing you to automatically cycle your database credentials without needing to change your application code. Access to these secrets are controlled using IAM policies that you can assign to your functions, giving fine-grained, least privileged access only to the specific functions that need it. Now that covers secrets, but what about general application configuration? Things like feature flags or non-sensitive settings that don't require that same level of permission control. Well, that's where AWS App Config comes in, which is a capability of AWS Systems Manager. An app config allows the creation, management, and deployment of non-secret application configuration. App config allows you to define your application configuration in JSON, much like the app settings.json files, and then to deploy them changes using DevOps best practices. Things like blue-green deployments and automatic rollbacks are all included as standard with AWS App Config. When it comes to retrieving that configuration, you would then use API calls, much in the same way you would for Secrets Manager, and that gives you that same level of fine-grained access control if you need it. The combination of Secrets Manager and App Config provide an excellent base for configuring your Lambda functions. As you can see in the bottom method in the screenshot on the right, the JSON data is read from App Config, and an instance of iConfiguration is created that can then be injected and used in the same way you'd use the iConfiguration interface in your REST APIs today. An important part of Lambda is networking. So as you start on your modernization journey, it's likely that you still have some element of traditional infrastructure that you need to connect to. The MySQL database being a great example of this. For that reason, it's really important to understand how networking in Lambda functions work. So Lambda functions are always deployed into a VPC that is owned by the Lambda service. If you need to access resources in a private subnet of your VPC, you need to facilitate that network connection in some way. And to do that, when you deploy your Lambda function, you can specify a subnet and a security group to use. On deployment, the Lambda function gets assigned an elastic network interface within your VPC, and a connection is created between that elastic network interface and a VPC to VPC NAT from the Lambda service VPC. What that means is that elastic network interface will actually take up an IP address in the CIDR range for the subnet that you deploy into. And it's important to remember that if you then run out of IP ranges in that CIDR block, then no new Lambda functions will be able to be deployed. It's also important to remember, if deploying into a VPC, that you still need to facilitate any network routing to access any third-party APIs or SaaS services, and even some public AWS services like S3. So that covers dependency injection, application configuration, and networking, but at some point you're actually going to need to get this code into production. So the AWS toolkit for Visual Studio comes with some built-in tools to manually deploy Lambda functions from within Visual Studio itself. But as you move to production and start to build deployment pipelines, you're going to need a way to automate the deployment of your functions. AWS provides a range of options to handle this, two of which I'm going to cover today. The first is the AWS Cloud Development Kit, or CDK. CDK allows you to define application infrastructure using programming languages you're familiar with, like .NET. You can build your infrastructure using .NET code, which is pretty cool. For serverless specifically, it allows developers to define both the application code and the APIs and Lambda functions that will run that application code without needing to learn a new language or framework. CDK also comes with some built-in constructs to allow easy compilation and deployment of Lambda using AWS best practices. CDK simply compiles your infrastructure as code into a CloudFormation template, which is then deployed to your AWS account using the CDK CLI. The second, and my personal favourite way of developing serverless applications, is the Serverless Application Model, or SAM for short. SAM is an open source framework for building serverless applications. It provides shorthand syntax to express functions, APIs, databases, and event source mappings. With just a few lines per resource, you can define the application you want and model it using YAML. It adds some extensions on top of standard CloudFormation to simplify event mappings, APIs, and permissions management for serverless specific applications. So here's an example of a Lambda function and API defined using CDK. As you can see, a new function is created using a function object. And as part of that initialization, a set of function properties are provided, including the location of the function code, any environment variables, and the assembly, class, and method used to execute the function. A new REST API is then created, and resource endpoints are added to that API. In this case, a create resource that will be a post method. An integration is then added to that resource, and that's what links the Lambda function to the API. So while CDK is great for efficiency, as it allows developers to use familiar language and tooling, the CDK is built to be generic. And because of that, this configuration will become a lot more verbose and lead to duplicated code when building serverless applications. SAM, on the other hand, is built specifically for serverless. There is a deep dive session later today called Your AWS Infrastructure is Code with the AWS Cloud Development Kit that I would recommend joining if CDK looks interesting to you. Now, here's an example of a SAM template, and if you're familiar with CloudFormation, this will probably look pretty familiar. I've pulled out two specific sections of the template to talk through in more detail. The first is the global section. This allows you to define common properties across all of your Lambda functions. Things like the framework, timeouts, environment variables, and the networking configuration can be defined once, simplifying the definition of the resources themselves. I've also specified the deployment method, in this case using a canary deployment that will shift 10% of the traffic to the new version before cutting over completely after 5 minutes. As part of this deployment preference section, as well as a type, you can also define a list of CloudWatch alarms that, if triggered, will automatically roll back your deployment to the last good version. When it comes to defining the function itself on the right, that content's then simplified due to that initial global configuration. The URI simply specifies the local folder, which contains the project file for your function. The handler defines the assembly name, class, and method to be used when invoking the function. The policies section is one of my favourite parts of using AWS SAM. SAM comes packaged with a set of policy templates that allow you to add common IAM policies to your function. Instead of complicating your template with manually configured IAM roles and policies, SAM can automatically add the correct IAM permissions and actions based on the template you define. In this case, the ability to read the secrets and app config data that we covered earlier in this presentation. The final section is the events section, and this is how we map the events to the invocation of the function. In this case, we set the event type to be an API call and the path and HTTP method used to invoke the function. There's no requirement to manually define an API as part of your template. SAM will automatically create an API gateway using best practice once it sees that at least one of your functions is using API gateway as an event source. Now, you can manually define your API as well if you need to add any additional configuration or complexity on top of what comes out as standard. SAM also comes with a command line interface that's used to initialize, build, and deploy your functions. When you're starting a new project with the SAM CLI, you can run the SAM init command, and that will take you through a tutorial that will give you a pre-configured .NET ready SAM application. When it comes to deploy that application, you'd first run the SAM build command, and the build command will go through your template and compile your .NET code for all of your functions and create a zip file per function. When it comes to you running the deploy command, SAM will upload all these individual zip files to S3, generate a CloudFormation template using them S3 zip locations, and then deploy that CloudFormation to your AWS account using CloudFormation. One of the common things I get asked when using .NET with Lambda is cold starts. A cold start is the time required for the execution environment to be created when a function is invoked for the first time. Behind the scenes, Lambda creates that micro virtual machine that's used to execute the function code in an isolated environment. For object-oriented languages like .NET and Java, this has typically been a common drawback when compared with languages like Node or Go or Python. Once the execution environment is there, it can then be reused for future invocations, which is known as a warm start. But as we discussed earlier, after a period of inactivity, that execution environment will be shut down, meaning the next execution will then require another cold start. If you look around the internet, there's reports of this period of time of inactivity being 5 to 60 minutes, but the Lambda service team provides no SLA for that time a Lambda execution environment will stay active for. With .NET 6, Microsoft and the Lambda service team have made huge stride forward to enable better performance on Lambda. The two tables on screen are taken from a set of benchmarking repositories available on GitHub across a range of different programming languages. The top screenshot is for .NET and the bottom one happens to be for Go. As you can see, when .NET 6 native compilation is used, which is the second row from the bottom, the code and warm start times are actually comparable to Go, further closing the gap between using .NET and some of the non-compiled language that traditionally were much faster when using AWS Lambda. The GitHub repo at the bottom of the screen can be used to find the .NET benchmarks, as well as links to all the other languages that you can then have a look at. So when working with Lambda on AWS, there are a number of tools that I just want to call out in some more detail. The first of which is the AWS Microservice Extractor for .NET. So the Microservice Extractor simplifies the process of refactoring your monolithic applications into independent services. You can modernize and transform your applications with an assistive tool that analyzes source code and runtime metrics to create a visual representation of your application and its dependencies. You can also extract the code base into separate projects that teams can develop, build, and operate independently to improve agility, uptime, and scalability. There's another session this afternoon called Splitting a Monolithic ASP.NET MVC application into microservices that goes into the AWS Microservice Extractor for .NET in much more detail. So I'd highly recommend checking that out if this looks of interest to you. One of the most exciting innovations I've seen recently for .NET and Lambda is the .NET and Lambda Annotations Framework. It's currently in preview and the blog post at the bottom was actually only published a couple of weeks ago. The Annotation Framework aims to make the experience of writing Lambda feel much more natural in C#. The aim of the framework is to take function code as defined on the left and remove a lot of that boilerplate code to allow the function to focus only on the business logic itself. As you can see in the example on screen, this takes an add function that includes method and parameter validation, checking the request and returning a new response object, and moves that to a method that only contains the business logic. The Annotations Framework uses a C# feature called source generators to generate code that translates from the Lambda programming model to what we see in the second example. Currently, the library is focused on Lambda functions for REST APIs. You can also write Lambda functions with just that Lambda function attribute to take advantage of the dependency injection integration. And we'd like to expand the annotation framework to simplify other event sources as well, like S3 and DynamoDB events. Currently, the framework has implemented some common HTTP attributes, including from header, from body, and from query. But we're really looking for some community engagement to help drive the roadmap for the annotations framework so that we're solving the problems that you as customers are facing. The framework also adds functionality to simplify the dependency injection configuration. Instead of defining a custom class and writing a method to manually create your dependency injection container, the framework adds a Lambda startup attribute, which can be used to define a method to be called on startup. This again simplifies the route to modernization, as you can now almost copy and paste your existing startup class from your .NET API and add a simple attribute for Lambda to then use to start running the same startup code for Lambda. So I always like to leave these kind of presentations with some next steps or some actionable takeaways that you can take. And the first one is to find your serverless developers. What I mean by that is most customers we talk to and most development teams we talk to are using Lambda in one way or another. With the range of things you can do with Lambda, from simple batch scripts and automation tasks right through to machine learning, in most cases teams are using Lambda already. That may be for a simple alerting workload, maybe for some data processing, and maybe just for a reactive part of your system that just needs to react to a certain event. So find the developers you have internally already, and with them developers, build a tiger team. And using a service like the microservice extractor, maybe pull out part of your monolith and use that as a proof of concept or a lighthouse project just to see what that modernization approach would look like and what kind of value, scalability and resilience you can start to achieve if you use AWS Lambda. And with that, I want to say thank you for listening. I'm always really interested to talk to the development community, so please feel free to reach out on either Twitter or LinkedIn if you have any questions or want to follow up with me personally. I've also included a link at the bottom there to a blog post that I wrote for the AWS Compute blog, and that provides a lot more written detail and links to the GitHub repositories and samples that I've talked through in this presentation. Thanks for listening and enjoy the rest of your conference.